My name is William Dunn, and this is going to be my Lab 2 report. Alright, so for an introduction, Lab 2 uses the same physics concepts as Lab 1, except it also adds the idea of using a charge distribution and calculating the electric force between two charge distributions, instead of just using 2-point charges to calculate this force. So this lab mostly uses the concepts of electric charge, force, and field when we're charging the tape, floating one tape above another tape, and determining the sign of the tape's charge. It uses the concepts of Newton's second law and gravitational force because since electric force and gravitational force are the only two forces acting on the upper tape, we can set these equal to each other because they act in opposite directions with equal magnitudes. And then it uses the concept of charge distributions and the electric force due to a charge distribution when calculating and modeling the charge and the electric force in GlowScript. So the measurement and the observations, I use the same measurements and observations as the first lab because the procedure is the same. So the tape length is going to be 20 centimeters, which at 1 gram per meter is going to have a mass of about 0.0002 kilograms. The distance at which the tape floats is going to be 1.5 centimeters, which is about 0.015 meters. And then the observations that were important in this lab are that the tapes repel each other, which means they have identical charges. One tape is attracted to a negatively charged pen, which indicates that the tape is positively charged. And then because the tapes are easily discharged by touching objects or hands, it indicates that the charge on the tapes is relatively weak. My data and calculated values are below. So the gravitational force on the tape is going to be about 1.962 times 10 to the negative third power newtons. K, our electric constant, is going to be equal to 9 times 10 to the power of 9. The area of the tape is going to be 0.2 meters times 0.02 meters, or 20 centimeters times 2 centimeters, because the width of the tape was 2 centimeters, which is going to get us 0.004 square meters. The area of an atom is going to be the length of an atom squared, which is going to be 1 times 10 to the negative 20th power meters squared. And then the number of atoms on one tape, we're going to divide the area of a tape by the area of an atom, and that's going to give us 4 times 10 to the 17th power total atoms. Using Newton's second law, as I described earlier, we can set the electric force equal to the gravitational force because they are the only two forces acting on the upper tape. So the charge on the upper tape generated from our coded model in GlowScript is going to be about 1.88 times 10 to the negative 8th power coulombs. The electron deficiency, we're going to divide this charge by the charge of one electron to get 1.173 times 10 to the 11th power electrons deficient. And then the ratio of deficient to total, we are going to divide the number of deficient electrons by our number of total atoms, which is going to give us 2.93 times 10 to the negative 7th power. So for the code, assumptions made were ignoring the air resistance on a moving object and assuming that each U-tape made had about the same amount of charge evenly distributed along the length of the tape. My code is below, along with a link to the code. So this code demonstrates the electric field line charge and electric force functions, which were used to create the lines of charges used in the distribution. And then the electric field function was used to find the electric field at the location of the upper tape by the lower tape. The electric force function was used to calculate the force on the upper tape by the lower tape. And then the code will output this display. The green arrows represent the electric field at the location of the upper tape by the lower tape. The white arrow represents the electric force on the upper tape by the lower tape, and the yellow arrow represents the gravitational force on the upper tape. In conclusion, this lab demonstrates that using a series of point charges or a charge distribution rather than just a single point charge is a more effective model to estimate the charge on the tape. So the charge I found in this lab using the charge distribution was about 1.8 times 10 to the negative 8th coulombs, which is higher than the 7 times 10 to the negative 9th coulomb charge that was calculated in lab 1. This difference is likely caused because there's a lot more additional calculation necessary when you're using two charge distributions instead of two single point charges, because you have to look at the effect of every piece of the charge distribution from the bottom tape on one piece of the charge distribution from the top tape, and do that for every piece of charge distribution from the top tape, and then add all of those together. The distribution model is going to be more accurate because it more closely models the actual number of point charges on the tape, which is much, much higher than the 10 point charges used in this distribution, but it's still an order of magnitude higher than a single point charge, which gets us closer and closer to actually modeling what's really going on in the tape. Therefore, the distribution is a more effective estimate than the single point charge. Thank you.